Welcome everyone. Today we're going to look at a lesson on percent yield, which is another component in stoichiometry. Sometimes finding percent yield involves finding the limiting reactant. You see, you learn that the theoretical yield is what you're supposed to make. It's also known as the expected yield. When you perform a lab, the students, what they produced in the lab is known as the actual yield. You see, we are not perfect. We don't always make what we're supposed to. Sometimes when we're transferring chemicals, sometimes you lose a little bit and you don't make the exact amount you're supposed to, which is known as the theoretical yield. Let me use my hamburger analogy. Let's say you had 10 burger patties and you had plenty of burger buns. If you all know, according to that information, you're supposed to make 10 hamburgers. So you're on the grill, you're barbecuing, making the hamburgers, and inadvertently one of them falls onto the ground and it gets all dirty. Well, what you're going to do is you're going to discard that patty, and instead of making 10, you're going to end up making 9 burgers because you ended up losing one of them. So what you actually made would be 9 burgers. You were supposed to make 10 with the amount that you were given. So if you divide the actual yield, the 9 burgers, by the 10, which is what you were expected to make, and you multiply by 100, you ended up making 90%, which is the percent yield. Now this concept can be applied in chemistry as well. Take a look at this example. Here you're reacting 11.5 grams of carbon. So let's put here 11.5 grams. And we are reacting it with 114.5 grams of copper 1 oxide, which is Cu2O. Now, according to this, you did this reaction and it says that you obtained 87.4 grams of copper. So this is the product that you made. We're going to call this B. You see, the number that you got here, 87.4 grams, is what you obtained in the lab. This is what we call the actual yield, the student answer. So what we're going to do is we're going to find out what we were supposed to make of copper if we were perfect. In other words, I want you to set up the problem solving for copper as your unknown, and we want to find the theoretical yield of copper. Now notice there are 2 givens. Therefore, this problem is more complex. You have one reactant here, which is given at 114.5. You have another reactant here, we'll call it A2, for carbon at 11.5. So what we're going to have to do is we're going to have to do this twice to figure out who is the theoretical yield. So first we start with the first reactant, and we're going to have to convert this into moles. So we got 114.5 grams of Cu2O. We got 2 coppers, 1 oxygen. From the periodic table, this is 63.55. We're going to multiply that by 2. You get 127.1. Oxygen is 16. Add this up and you get 143.1 grams per mole. So the first step is to divide by 143.1 grams per mole. We're going to change grams of A into moles of A, and you end up getting 0.0014 moles of Cu2O. Once you convert to moles, the mole ratio between B and 1A is 2/1. And then multiplying by 2, you get 1.6003 moles of copper. To go from moles to grams, you multiply by the atomic mass of copper, which is simply 63.55, and that's obtained from the periodic table, grams per mole. So when you multiply by the molar mass or atomic mass of copper, and we're going to round this to 4 significant digits because the 143.5 the 114.5 has 4 significant digits. We get 101.7 grams of copper. We're going to put a little box here. Okay? Now, here's what I'm going to do. Let me erase this to give us a little bit of room so that we can do A2 right here in this space, and we can use that to compare. So the other reactant, you got 11.5 grams. We're going to divide that by the atomic mass of carbon, which is just 12.01 grams per mole from the periodic table. And when you do this, you end up getting 0.9575 moles of A2, which is carbon. The mole ratio, B over A2, happens to also be 2 over 1. And here you get 1.9151 moles of B, which is copper. The last step, because it's the same B, you're going to multiply by the atomic mass of copper, which is 63.55. And this time we're going to round to 3 significant digits because of the 11.5. And I get 122 grams of copper. So we are ready to make a comparison. When I did A1 to B, or Cu2O to copper, I got 101.7 grams. When I did A2 to copper, which is carbon to copper, I got 122 grams. Remember that the lower one is the one we're going to keep. We throw out the higher one. So when they ask you who is the theoretical yield is right over here. It is 101.7 grams of copper. That is also known as the expected yield. If we were perfect, that's how much copper we were supposed to make. Now they also want who's the limiting and the excess reactant. Well, A1 was this first reactant over here, Cu2O. He is our limiting reactant. That means that the one that gave us the higher answer, which was carbon, that's the excess reactant. Now to find the percent yield, we're going to do a ratio of actual yield over theoretical yield, and then we're going to multiply by 100. Well, the actual yield was given in the question. The actual yield was 87.4 grams. We just found the theoretical yield at 101.7 grams. Grams are going to cancel. You're going to multiply by 100. Now, we're going to round to 3 significant digits because of the 87.4, and we end up getting 85.9% as our percent yield. Now, we can check this problem over here. You can see that here is A1. Actually, they used this one as A1, and this was A2, so they did it backwards. But you could see that as they work it out, they're showing you the mass-to-mass setup. I'm going to go to the next page here so you can see here is A1. That's what we used as our first mass-to-mass. They did this one as A2. And here are the 2 answers they obtained. Notice that the lower one is 101.7, that's highlighted in yellow, and that would be your theoretical yield, which goes on the denominator of the percent yield equation. And then the limiting reactant is labeled in blue. That was Cu2O, copper 1 oxide. And then to find percent yield, notice the setup here at the end. It's actual over theoretical times 100, and they rounded to 3 significant digits and got 85.9%. Now here's a skill builder. I would like you to try this one. The equation is already given to you. It's balanced. Okay, notice they're telling you have 185 grams of Fe2O3, which is iron 3 oxide. You're reacting it with 95.3 grams of carbon monoxide. And the product that you're making here is 87.4 grams of iron. So determine the limiting, the excess reactants, who is the theoretical yield, and go ahead and find the percent yield for this problem. I'm going to go ahead and pause the video, and then when you are ready, we'll come back and work it out together to see how you did. All right, so let's check the problem. Well, we got here, we'll call this A1. Notice you got 185 grams of this guy. You got 95.3 grams of this guy. This is A2. This is what we're making. The student made 87.4 grams. So this is the actual yield. This is what you made in the lab. The question is, let's call this B for the unknown and see what we were supposed to make, which is the theoretical yield. Let's look for that. Now, because there are two reactants and we have the masses of each, we're going to have to do two mass-to-mass problems to figure out who's the limiting reactant. So first we'll do A1. A1, we have Fe2O3. We got 185 grams. The first step is to convert to moles. So we need to find the molar mass of Fe2O3. I'll do it down here. There are 2 irons, 3 oxygens. Iron is 55.85. Multiply that by 2, you get 111.7. Oxygen is 16. Multiply by 3, you get 48. Add that up and you get 159.7 grams per mole. So we're going to get the grams of Fe2O3 divided by 159.7, and our objective is to change that to moles. We get 1.1584, and that's moles of Fe2O3. Now that we're in moles, the mole ratio between B and A1 is 2/1. So we're going to end up just multiplying by 2, and you get 2.3168, and that's moles of Fe. Now, Fe is just an element. Remember to ignore coefficients. Do not multiply by 2. There's only one Fe there, and it's 55.85 grams per mole. Very important you don't multiply by 2. So to go from moles to grams, you multiply by the molar mass of the unknown, or B, and that happens to be iron, okay? And you end up getting 129 grams of Fe, and we will round it to 3 significant digits. Now, we still got to do another step. So let's erase this piece here so we have room to compare the other mass-to-mass problem. We'll call this A2. And this time we got 95.3 grams. We got to divide it by the molar mass of CO. Well, C is 12.01. O is 16. Add that up, and you're going to end up getting 28.01. So let's put that here, 28.01 grams per mole. So let's change 95.3 grams divided by the molar mass of A2, or carbon monoxide. You get 3.40236, and that's going to give you moles of CO. Now the new mole ratio, B over A, notice it's 2/3, so you got to multiply by 2, then divide by 3, and you're going to get 2.268, and that's going to be moles of Fe. And the nice thing about the last step, it's the same B, which is iron. You're going to multiply to go from moles back to grams by 55.85, and when we round this, it's 127 grams of Fe. Now the two answers are very close. However, we always will keep the lower of the two. We're going to throw out the higher answer. So the lower answer here is 127. This is going to be our theoretical yield. Okay? Now, which reactant did we use to get the 127? Well, it was A2, or carbon monoxide. So carbon monoxide in this example will be our limiting reactant. And that means that Fe2O3 in this reaction will be our excess. Now, when the students did this lab, they made 87.4 grams of iron. So if we get the actual yield and divide it by the theoretical, which we now have all the information, and multiply by 100, you get a percent. Well, The actual yield made by the students, they produced 87.4 grams. We found out that if we were perfect, the theoretical yield or expected yield should have been 127 grams. The grams are going to cancel, there are no units. When you multiply by 100 and round to 3 significant digits, you end up getting 68.8%. Now, when you do these percent yield problems, the closer you are to 100%, the better your lab technique. You want to be close to 100%. Okay? So again, percent yield is found by getting the actual yield, which is the student-made answer in the lab, and you divide it by the theoretical or expected yield, which, as you saw, is found by doing the math, by doing the stoichiometry. Sometimes, like in these problems, you have to do two mass-to-mass problems to figure out who's the limiting and excess reactant. And once you do that, you set it up, multiply by 100, and you get your percent yield. So that will conclude this lesson on percent yield. Good luck.